lecture we look at safety stock computations in Kanban. In the previous lecture we looked at this formula using which we computed the number of Kanbans. So, here n is the Kanban size, S is the safety stock that we give, D is the demand, and F is the lead time or the fraction of demand that we are considering. So, if we take an example and say that the demand is 100 per day comprising of 8 hours per day, lead time in this case is 2 hours, which is 0.25 for this example. So, this will become 0.25 into 100, 25 plus S by 10 if n is equal to 10. Now, this S is the safety stock that we provide. So, if we assume that this S is 10% of the lead time demand, then this will become 27.5 by 10, which will be approximated to 3 Kanbans. So, this led us to how do we fix this S or safety, or how do we fix this 10%. So, if we assume a 10% safety stock, then we get 3 Kanbans in this example. We looked at some ways of fixing the safety stock. One is to try and take a fixed percentage such as 10% for the computation, and then as the system progresses or as we start implementing the system, we get better control over the withdrawal and the Kanban system, and the percentage can actually come down from 10% as we implement this system. The second one is to decide a predetermined service level. Say we will have a 95% service level, say, and once we have 95% service level, then the safety stock will be taken as Z into sigma if we assume that the distribution is normal. So, Z comes from the normal table and sigma is the standard deviation of FD or the lead time demand. If we use 95%, Z becomes 1.645 times sigma. This 1.645 comes from the standard normal distribution. So, if we say in this case that the standard deviation of the lead time demand, let us say, is 2, if sigma is found as 2, later we will show a procedure as to how we compute the sigma. So, if sigma is 2, then we would have service S is equal to, safety stock will be equal to 1.645 into 2, which will be 3.29, and K will become 25 plus 3.29 by 10, which will give 3 Kanbans. The third way to do is, for a given shortage cost, we find out the area under the normal curve, and then we use the z is computed from the normal curve for a given Cs, for a given shortage cost, this is computed. In this example, the service level was predefined. So, based on the service level, the z was computed. Here we looked at the standard normal distribution. And if we said that the service level is 95%, then we are going to find out z for which this area is 0.95, and then using that z, we computed the number of Kanbans. Here what we do is, we, for a given value of the shortage cost, we can compute the z value, and then from the z value we can compute the number of Kanbans. We will now do that derivation. For this derivation, we go back to probabilistic inventory models, where the total cost of inventory is given by D by Q into C naught. D is the annual demand, Q is the order quantity, C naught is the order cost per order. So, D by Q into C naught will give us the total ordering cost, plus Q by 2 into Q by 2 is the average inventory that we hold in this system, plus there will be a safety stock. So, if the reorder level is R minus expected value of lead time demand will be the safety stock that we have in this system. So, the reorder level will be more than that of the expected value of lead time demand, and this represents the safety stock. This safety stock is always carried, and therefore, it is not divided by 2. So, R minus expected value of lead time demand into CC into inventory holding cost, plus the shortage cost. So, in this shortage cost, now S bar of x is the probability of shortage happening in a cycle, which means the demand exceeds the, now S bar of x is the expected shortage, S bar of x is the expected shortage, it is not the probability of occurrence, it is expected shortage. So, it is the expected value of the shortage. So, S bar of x into Cs is the shortage cost per unit short into D by Q, because D by Q is the number of cycles in a year. So, S bar of x is the expected shortage in a cycle, Cs is the shortage cost per unit short, D by Q is the number of cycles in a year. The best value of Q and R are obtained by differentiating this expression. Dou Tc by dou Q equal to 0 gives minus D by Q square C naught plus Cc by 2 minus D by Q square S bar of x Cs equal to 0, from which Q equal to root of 2D C naught plus S bar of x Cs divided by Cc. This expression is similar to the economic order quantity formula except for a term involving S bar of x, which is the expected shortage. Now partially differentiating this with respect to R, dou Tc by gives, this will be a constant. So the first time R comes in is here, R plus differentiating with respect to R, this will be Cc plus Cs into d by q to dou by dou R of S bar of x. So plus dou by dou R of S bar of x into Cs into d by q equal to 0. So this will give us Cc plus Cs d by q dou by dou R of. Now S bar of x is the expected shortage in a cycle. So this will be integral R to infinity x minus R fx dx. Now R is the reorder level, x is the actual demand. So when the demand exceeds the reorder level, the shortage is x minus R. The probability of occurrence of that comes from the distribution. So x minus R fx dx. So this when we differentiate, we will get Cc minus, the minus comes from this Cs d by q integral R to infinity fx dx, from which integral R to infinity fx dx is equal to qcc by dcs. Now this represents the probability of shortage, probability of shortage is given by qcc by minus qcc divided by dcs. Now if we look at the units, q is demand, q is the order quantity, this is rupees per unit per year, this is in units. So this is rupees per year, this is rupees per unit short, this is units per year. So this is also rupees per year. So qcc by dcs does not have any dimension, it is just a number, and 1 minus qcc by dcs is the probability of meeting the demand. Is the probability of meeting the demand. So this is how we derive this 1 minus qcc by dcs. So from this we have probability of meeting the demand or no shortage is equal to 1 minus qcc by dcs. Now this is given in the slide as 1 minus in by cs mu, where the notations are now changed for the Kanban system. So we write this as in by cs into mu, in by cs into mu. Now n represents the q, so this is the container size, I represents the carrying cost, cs represents the shortage cost, and mu represents the demand. Now in order to be consistent, this is in units, this is rupees per unit per year or rupees per unit per hour or rupees per unit per time period. So, together this will be rupees per unit. This is rupees per unit short, this should be rupees per, so this n is size which is units. So, rupees per unit per year multiplied by unit is equal to rupees per year or per time period. This is rupees per unit short, so rupees per unit, so this should be unit per time period. So, mu is actually the demand for the item. So, if we take this formula and then we go back and substitute here. Now, for our example, so probability of meeting demand or no shortage will be 1 minus. Now, we assume a Kanban size of 10 by, if we assume that our daily demand is 100 per day, so mu will be 100 per day. If we say that this is CS is 10, CS is 10, and if the inventory holding cost is, let us say, rupees 8 per unit per day, say this is say inventory holding cost is rupees 5 per unit per day. So, this is rupees 5 per unit per day, this is 100 units per day. So, this will be 1 minus 5 by 100, which is 0.95. So, given the CS, we would calculate this 0.95. So, once again we go back to the normal distribution and find out Z, for which probability of meeting the demand is 0.95. So, Z will become 1.645 and the number of Kanbans, the safety stock will be 1.645 into 2, which is 3.29, and the number of Kanbans will become 3 as in this example. Now, here the mu is actually taken from the given data and is assumed to be 100 units per day. Now, there is another fourth method by which we actually compute the mu depending on what actually happens in the factory. To explain that, we take another example. Now, we have shown some data which says for a single item, the last 10 withdrawals and the last 10 replenishments are found to have taken place in the times given in the table. For a 95% confidence level, assuming normal distribution, find the safety stock and the number of Kanbans. Also compute the Kanbans for CS equal to rupees 5 per year. So, there are 10 withdrawals and 10 arrivals are given. So, from the 10 withdrawals and 10 arrivals, the time taken between a withdrawal and the corresponding arrival which replenishes the withdrawn Kanban is taken as an instance of a lead time. So, the 10 lead time values calculated are 65, 82, etc. and for the 8-hour shifts ends at 1600 hours. So, the mean and standard deviation of the lead times calculated from these 10 values are 1.37 hours and 0.36 hours. So, we assume that mu of the lead time, mean of the lead time and sigma lead time from calculation comes from, for example, the 65 time units are taken from this. Day 1 time 8:10, day 1 time 9:15 is 65 time units. Like this, the 10 time units are chosen their mean and standard deviation is 1.37 hours and 0.36 hours respectively. So 1.37 hours is roughly about 80 minutes and 0.36 hours respectively. Now what is the demand? So the demands are calculated based on the withdrawals. We observe that 10 Kanbans have been withdrawn during a time period of 9 hours. So demand is 9 is 1.11 Kanbans per hour. So 10 Kanbans are taken in 9 hours. So demand is equal to 10 by 9 Kanbans per hour, 1.11 Kanbans per hour, which is 11.1 units per hour, because each Kanban has 10 units. So 11.1 units per hour. So mean lead time demand. So mean lead time demand mu LTD, lead time demand is equal to 1.37 into 11.1. So lead time demand is 15.2 units. Now sigma of lead time demand. So sigma of lead time demand is 11.1 into 0.36 hours. So 11.1 into 0.36, this is 4 units. So at 95% confidence level, if we have 95% confidence level, now Z is equal to 1.645. So mu plus Z sigma is 15.2 plus 4 into 1.645, which is 21.78. So this is approximately 3 Kanbans. So in all the 4 instances of calculation, we had the same value as 3 Kanbans, but the way by which we calculated in each of these instances is very different. So in the very first one, we assume a fixed number of fixed percentage for the safety. In the second one, we assume a certain service level, and based on the service level we did the calculations. The third one, we took a CS, a shortage cost, and based on the shortage cost we borrowed results from inventory models and computed that probability of meeting the demand in this case turns out to be 0.95, and then we went into the normal distribution and got it. In the fourth one, this is very similar to the second one, because the 1.645 is taken from a 95% service level. So here we do not use the shortage cost, instead we use the service level. The only difference of course is the demands and the standard deviations are now computed. So we have shown a way by which we compute the standard deviation. Here we assumed that sigma is equal to 2. Here we computed the sigma, and sigma actually happened to be 4 units in this case. So all these computations help us in trying to find out the service or the safety stock that we have to include in this calculation. Now mu plus Z sigma will directly replace Fd plus S. This mu is mu LTD. Lead time demands mu will directly replace Fd plus S and divided by n. So mu will be the Fd, this is the S, and n is 10. So we get 3 Kanbans in this computation. So this is how we can compute the safety that is to be incorporated in the Kanban calculations. Then we move into a couple of other models for Kanban, which is this. Now, we described in an earlier lecture that the manufacturing cell could be like this, following unidirectional flows. It might be handling multiple products, we could call them A, B and C. Etc. We also said that let us say if A is being done, then one Kanban of A is completed and there could be an area outside where these Kanbans are available or containers or some kind of a container storage area. So, when one particular item is completed, then now this has to go and it has to be replenished. Now, how do we choose the next item to be replenished is another model that will dictate the completion times of the various items that we are looking at. So, some simple thumb rules are complete all the containers of the last processed item. Another rule could be first come first served. The third could be shortest processing time. The fourth could be earliest due date. Fifth could be a cyclic rule, and the sixth would be to choose one which has maximum number of Kanbans. So, these are some of the rules that we could use, and depending on the rule that we use, the performance of the system is defined. So, we just illustrate it with an example. A manufacturing cell processes 3 parts A, B and C. It has just completed B. So, it has just completed B. So, B is coming out of this. The waiting Kanbans in the order of arrival are A B, A C, B A. A B, A C, B A are all here in the order of arrival. A B, A C, B A. The processing times for A, B and C are 20, 18 and 15. So, processing times are 20, 18 and 15, and the due dates for these 6 Kanbans are 20, 30, 25, 20, 30, 25, 50, 45 and 40. So, how do we choose the first one? So, we want to complete all the containers of the last processing, which is our first rule. Since B has been completed, we will take these 2 B's to begin with. We will take these 2 B's to begin with. So, first one will say take B and B. Second one would be first come first served. So, this came first. So, take A and I will say take A1. Here I will say take B2 and B5. The third rule would be the one based on shortest processing time. So, we will end up looking at the processing times. C has the smallest processing time. So, take this C, take C3. The fourth one would be to do the earliest due date. So, if we take the earliest due date, we first look at this is the earliest due date. So, this corresponds to this. So, take A1, then the third one. So, A3, then this B2, then this A6, then B5 and then C4. What I mean by A3 is this A3 is this A6 is this A. There are 6 Kanbans waiting. So, I call this as A at position 6. So, A6, this is A at position 3. So, it is A3. Fifth one is if we look at a cyclic method and follow the cycle ABC. So, B is completed. So, we will take C first. So, we will do C4. So, this should be C4 and then followed by A. So, A1 and then B5 etc. So, the cycle will be B, C, A, B, C and so on. The last one is if I have choose the one which has maximum Kanbans. So, A has maximum Kanbans. So, choose A1. Now, each of this rule has a certain effect on the system. Now, this rule, the first one where complete all the containers of the last processed one will actually take us away from small runs. So, this will end up having slightly larger runs, because we will be continuously doing the B's till they are exhausted and then move to the other one. Now, in a way cyclic is the best in terms of single piece flow. This will produce items at very short runs. So, cyclic is a very good rule. Sometimes to meet due dates we start looking at earliest due date rules. So, EDD can still give us, as in this case, 2 consecutive containers of A to be processed, which actually takes us away from the idea of a single piece flow or a small or short run and so on. Choosing maximum Kanbans is again a very conservative rule which prevents an inventory build up of a certain item in this place. So, this is something which choosing shortest processing time, choosing maximum number of Kanbans are more of internal conveniences. So, if we have a large pile up of A, then we have to understand somewhere else that they are not following either a cyclic rule or the correct type of rule. But these dispatching rules also help us understand how the system is performing. So, simulation studies have been carried out which take into account the various dispatching rules and then try to model the system based on the dispatching rules to understand the performance of the system for various dispatching rules. Now, we look at one more model under JAT which talks about small lot production. Talk about small lot production. So, consider a cell making 2 items A and B. So, there are 2 items A and B that are made and 600 time units are available. We could take these as minutes, 600 minutes are available. The demand for each item is 60. So, A's demand is 60, B's demand is also 60. The total time to make a piece of A is 10 minutes with a bottleneck time of 4 minutes. So, 10, 4 and to make B it is 8 minutes with a bottleneck time of 3 minutes. So, we could assume that there is the cell, there are multiple machines, there is unidirectional flow. So, when it is making 10, the sum of the individual times are such that the maximum is 4 and the total is 10, whereas when it is making B the total is 8 and say the maximum is 3. So, this is written as 8, 3. The changeover time from A to B and B to A is 20 minutes. Changeover time is 20 minutes. Find the minimum batch size for A and B. consider that 2 and 3 operators are available and the setup time is reduced to 10 minutes. So, 2 operators are available and 3 operators are available, setup time is reduced to 10 minutes. So, 2 operators are allotted to A and B. So, we look at a case when case 1 there are 2 operators. So, if 2 operators are allocated when we make A, then this is the maximum time, this is the bottleneck time. So, time taken to make A is 10 by 2, which is 5 minutes, and time taken to make B is 8 by 2, which is 4 minutes. If we assume that there is rabbit chasing, so total is 8. So, when there are 2 operators at steady state, 8 by 2, 4 minutes is the time for each of them. The demand is 60, so 5 minutes per piece. So, this requires 300 minutes and this requires 240 minutes. Now, if we assume that it is already set up for A, then we can start producing A. We can produce 60 of A, we produce 60 of B, and the time taken will be 300 plus 20 to change over plus 240, which is equal to 560 minutes. Now, we can call this as case A. Now, we look at case B. Now, with 2 operators working for A and B, we require a processing time of 540 units. So, 60 units are available with which we can make 3 changeovers. So, we can now produce A, B, A, B, and if we do that, so the production batches will be 50, 30, 30, 30, 30. So, we first to produce 30 we need 150 plus a changeover of 20 plus 30 4s are 120 plus another 20 changeover plus another 150 plus another 20 changeover plus 120. So, this will be 150, 170, 290, 310, 460, 480 plus 120 is 600. So, we use up all the 600, but we are able to produce 4 lots of 30 each, whereas here we produced 2 lots of 60 each. So, if we use the time available correctly, then we will be able to get smaller run production. Now, if we consider 3 operators, now time taken to produce A will be 10 by 3, which is 3.33, but the bottleneck is more than that. So, time taken to produce A will be 4 units. Similarly, time taken to produce B, 8 by 3 is 8 by 3 operators is 2.66, which is smaller than the bottleneck time 3 or the maximum time 3. Therefore, the time taken will be this 3. So, B will be 3 minutes. So, time taken to produce 60 of A, 60 of B plus setup plus 60 of B will be 60 into 4 240 plus 20 plus 60 into 3 180. So, this is 440, we will be able to finish this. 4 into 60 is 240 plus 20 plus 180. So, now the time available is time required for manufacture is 240 plus 180, which is 420. So, 420 time units are required for the manufacture, 180 time units are now available and we can do 9 changeovers. So, we can do 9 changeovers, which means we can produce 5 batches of A and 5 batches of B. So, batch size becomes 12. Batch size becomes 12. So, we start with 48, 12 into 4 48 plus 20 plus 36 plus 20 plus 48 plus 20 plus 36 plus 20 plus 48 plus 20. So, this is the first batch, this is the second batch, this is the third batch, like that 5 batches are there and the total time will be 600. The most important thing is the batch size has come to 12 as against batch size will be 60 in this case. So, the batch size would become 12. Now, in the same case, if the setup time is not 20, but the setup time is 10. So, if setup time is 10, setup time is 10, the total in this situation of 4 and 3 operators for A and B, which gives us 4 minutes to produce A and 3 minutes to produce B. So, the time required is 420. So, maximum time is 600. So, 180 is available. If the setup time is 10 minutes, 18 setups are possible. So, if we create another 10 minutes from somewhere, we can have 19 changeovers, which means the batch size can become 6. Batch size can become 6. In some sense, this is a very good situation, because the changeover times are 20, the production times for the batch are 48, 36 and so on. But if we can create another 10 minutes, we can make it very tight and have very short runs of 6 of A followed by 6 of B, and that is done 10 times. So, the batch size reduces to 6. We could also look at maintenance and availability. So, now we could say for the same problem, here we assumed that 600 time units are available for the production. Now, if we assume that 800 units were available in the cell, but the cell is working at 80% availability, which means time available becomes 640. So, when time available becomes 640 and we consider 3 operators, so times for A is 4 units and time for B is 3 units, total processing time required is 420. So, now we have 240 units of time available for setup, and if the setup time is 20, then we could have for 240 we could have 12 setups. So, when we have 12 setups, then we could produce 6 times A and 6 times B, and the batch size will be now 10. Batch size will become 10. and if the setup time from 20 it becomes to 10, then the batch size will become 5. We have another aspect to this problem which says that due to TPM initiatives the availability increased to 90%, now compute the batch size. So, when the availability increases to 90%, now time available is equal to 720. So, we have more time available. So, let us go back and see what happens to the 2 operator case, 2 for A and 2 for B. If we take this case, total time required is 540, 540 is the time required. So, we have time for setup, time available for setup is equal to 180. If the setup time is 20, 9 changeovers are possible. So, 5 batches of A and 5 batches of B are possible. So, batch size is equal to 12. Of course, when the setup time is halved, the batch size will become 6. If we had 3 operators working there, then the time required is only 420. So, 300 time units are available. So, 300 by 20 is 15, 8 batches are possible. So, batch size is roughly 7.5, and here it will be 4 or 3.75 when the setup time reduces further. So, essentially what have we seen? Now, we have seen, let me also circle all the batch sizes. Ordinarily, we will be very happy with this, because with minimum operators, 2 operators minimum number, we have a little bit of time available for changeover. We use that, 600 minutes are available, we use 560, so we are happy. The only thing is that we are producing large batch size of 60 in this. Now, this if the only thing we can do is we can bring down from 60 to 30 when we allow multiple setups in the remaining time available. So, the best scenario is 30. Increasing the number of operators from 2 to 3 creates extra time available for changeovers, and automatically the batch size from 30 becomes 12, dramatically reduces to 12. So, and further reduction in changeover times can bring the batch size up to 6. So, from 30 we have moved to 6. Now, by making time available due to TPM initiatives, availability is increased, batch size comes to 4. So, these are the 2 or 3 important parameters with which we have control. One is the number of operators, setup time, and availability. All these 3 impact the batch size. So, if we want to make smaller runs, the batch size should be small. So, in order to do this, the availability has to go up, and we also in this lecture series have seen that TPM is an extremely important aspect of JIT systems. So, having good TPM systems increases the availability, which in turn helps us to achieve smaller batch size and smaller run. Reducing the setup times creates extra time available for setups, because of which smaller runs are possible and the batch size reduces. So, there is always effort in setup time reduction. Decreasing the number of operators either through automation or dedication or rabbit chasing would help us again create extra time. So, decreasing the number of operators increases the time required, increasing the number of operators decreases the time required. So, the number of operators is the constraint that we have, and these number of operators have to be used correctly, so that by constantly trying to reduce setup times and increase availability, small runs are possible. Many times the number of operators is also less and it is fewer than the number of machines that we have. So, this example helps us understand the role of these three parameters on the batch size, and the understanding that important initiatives such as setup time reduction and TPM impact the batch size and can help us produce smaller runs. Number of operators is a constraint which has to be handled judiciously, so that this is not affected by the non availability of operators. In the next lecture, we will look at CONWIP, which is another way to have manufacturing control in manufacturing cells and factories.